Kovar. We have Rafiul.
Farshid, Rahman.
Roberto Cavazos.
And we did the Selux end-of-life detector. We worked with a company called Selux Lighting to create a controller that would tell when the end-of-life was. So a quick overview on what the presentation is going to be. We're going to give you an intro and a background on what we're going to do. We're going to show you the power supply we used for this device. We're going to show you talk about I2C protocol for you. We're going to talk about the PIC controller that we used. We're going to talk about how we programmed it, some complications we ran into during it, some Bluetooth stuff that we did, Android application as well. This is not. Yes, we're having a little technical difficulties here. Yeah.
Change the resolution.
So a little background. Selux Lighting is a local branch company in Highland. They have a major company in Germany, and then there's just a smaller branch that worries about Canada and like South America and all that. And then they have a branch that's in Europe that does Germany and all that kind of thing. And then there's a branch in Germany as well. They're currently working with Samsung LED linear modules, which will replace a 4-foot fluorescent tube, which is about a 12-inch LED module. It has 42 LEDs on it. There's 7 sets of 6 LEDs in series. It's extremely bright. It has a constant current driver of 350 milliamps, and it fluctuates between 19 volts and 60 volts to run the thing, so that it maintains 100% at 350 milliamps always. All right. And the project. This is the intensity curve. The LED, when you first turn it on, it starts here, and it'll go up a little bit in its brightness, and then over time it decays and decays and decays, as it shows here. But the problem is, this is now getting newer technology to be more of a flat curve, but they want to know when it gets to this peak, how when it decays like 70% of what the max value was. That's the whole purpose of the project. And the dimming is actually unable to be seen with the human eye, but it needs like government regulation stuff for lighting, for hallways and stuff like that. It needs to be a certain brightness. All right, so what does this project do? It allows users to select either 30% or 50% decay of luminosity in the light. It reads the LED intensity and calculates a 50 or 70% value. It notifies the user once the LED has reached the end of life via a separate LED that's like an indicator, or it uses an Android application and sends it to the user's phone. Some engineering constraints that we use. Economic. It requires very inexpensive components to make, probably make the entire thing for under 30 bucks. Manufacturability. There's a limited amount of components in it, so it's very cheap, very simple to make, not too many things to do. You can put it right on a PC board and be ready to roll. Sustainability. It allows for maximum use of the module's life, because currently the regulations are pretty much every 5 years, throw them out, get a new one. And I think the device costs $800 each time. So now they're going to be able to go to 50, 100,000, 200,000 hours, depending on your application with heat loss and everything like that. And then environmental. It's will have you the accurate life detection will allow you to stop throwing them out when they're way too early to be thrown out, kind of deal. All right.
Alright, so in present day, as all you know, power is a very important element today. In past, actually, we didn't care about that much efficiency with power, but nowadays, everybody's pushing toward more efficient device. The government actually, they're in process of banning all the inefficiency devices, such as the incandescent light and other inefficient devices. So LED actually is very efficiency, so the government actually pushing toward that. It's actually go back. So there was, for powering device, there was several options we chose. We had to power the microcontroller and everything. So one of the options was obtaining the power from the main AC supply, and another option we had, since we had an LED driver which was a constant current, it gives you a 350 milliamp current, and we thought having some circuitry to like take that current and convert into whatever voltage we needed to power our microcontroller. And each option actually had some of its advantages and disadvantages with it. So our first option that we had to take the power from the main power source, there was some regulation and standard that we had to follow. And one of the things is it's actually not economical. For that, we would need a transformer, and we thought like, why spending some extra money when we could like go with our other option, just have some circuit and which would do the same job. And also some transformer could be like a little bulky, so it take up some space. So we wanted to make it as compact and more efficient as possible. Yeah, so this is the LED board and the LED driver we have, and in our circuit when we simulated, this is how we simulated it. This is the constant current source, which represent the driver itself, which provides 350 milliamp, and that's the LED, which is that.
Okay. When we're designing the power source for our project, with several options, as you mentioned, one of the options from taking the power from the LED driver, from the constant current source. There are some problem too. One of the problem is we cannot take more than 15 or 20 milliamp, because if we take more than 15 or 20 milliamp, it will significantly dim the LED light itself. So there are many voltage regulator available online that we can buy. We could have bought from online that could do the thing. We bought several LED driver and designed our voltage regulator, but the problem with those voltage regulator was it draws too much current. Sometimes it draws more than 50 or 60 milliamp. We didn't want that because we wanted to restrict the current to 15 milliamp. So we ended up designing our own version of a voltage regulator. This is a discrete using NPN and PNP transistor and some resistor. It does convert a voltage range of from 15 to 40 volt to a 3.7 volt without drawing more than 15 milliamp. It will not draw more than 15 milliamp. So we had another design for our project. This using a two comparator circuit. It takes some current from the driver and convert it to voltage. But there's another problem in here too. If it needed, it draws too much current. But if it takes too much current, it can dim the LED. For our project, for the microcontroller itself, we did not need that much power, but we expanded our project to Bluetooth, and depending on Bluetooth module, it can take a lot of power. For example, there are many different type of Bluetooth module in there. Some Bluetooth covers only 10 meter, and some Bluetooth can cover up to 100 meter. So if the range of Bluetooth is more, and if we added more things to our application, then it will draw more power, and which can significantly dim the LED light itself. So we didn't want it to dim our LED lights. So that's what the problem. When we're designing when we're taking power from the LED light driver from the constant current source, we had to work with a huge voltage range. The range was from 18 to 65 volt. So from 18 to 65 volt, it had to provide a constant 3.7 volt. It was possible to do that, but it actually takes more power from the LED driver, which dims the LED. And then we go toward.
Well, basically there was supposed to be a slide here which shows our final power supply that we designed, which was consisting of a transformer. So the reason we had to use a transformer to step down the 120 volt AC to our transformer, it stepped it down to a 16 volt AC, and then we had a diode and a capacitor which worked as a half wave rectifier, and the capacitor had a peak value of 20 volt DC. So then we had a voltage regulator, which was an adjustable voltage regulator, which when we were actually designing it, there was another voltage regulator with it, but at first we had the adjustable voltage regulator, which would, because we needed a 3.7 volt voltage to power our microcontroller. So And the only problem with the voltage regulator was it only works at a range from 7 volt to 16 volt DC. So and the peak value was 20 volt DC. So we had to put another voltage regulator, which was LM7812, which works from a range of 15 volt to 40 volt at the input, and then output it provides a constant 12 volt. So and that way our other voltage regulator, which needed 7 to 15 volts in order to work, so that was perfect for us, and which gave the 3.7 volt output that we needed to supply our microcontroller.
One of the key components for our project was the light sensor. A light sensor is a device that used to detect the intensity of light. It can be visible light, ultraviolet, infrared, or even a gamma radiation. But for our project, we needed a light sensor that can detect the visible light and follow the human eye curve, roughly follow the human eye curve. There are many different types of light sensor out there, photoresistor, photodiode, photovoltaic, and many more. So when we researched, we found out several light sensors that can do our job and roughly follow the human eye curve. Some of them has I2C built into it, and some of are analog. We bought all of them, like analog and I2C. One of the problems with I2C we had is we were working with that, and few days we come back and we see some of the chips were broken, so we had to go back to analog for a short period of time until we got some more I2C model. So that actually significantly delayed our project process at least 2 weeks.
All right, digital light sensors. This is actually the light sensor compared to a penny that we used. This got 6 pads on the backside that we had to solder to compared to a dime. So it was extremely small, extremely stressful because we'd have it in for about a month and then something would sneeze on it and break all the wires off. So we had to change it many times. We ended up going through about 6 of them through this project. All right. And it communicates via an I2C protocol, which I2C works at. We ran at 400 kilohertz per second. It can go at 100 kilohertz per second with this chip that we use. It works at 50, 60 hertz lighting ripple rejection, which is good for us, and it only used 600 microwatts of power, which was perfect for this whole little low power thing. It can detect human eye and IR light, but we use the IR light spectrum because if you use human eye, we have to do a huge amount of calculations between the 2 data curves, which we talked to our company representative, Brian Patterson. He said, don't even bother doing that, just use the IR, it'll work fine. All right, and so I2C protocol. It's, like I said, it's a 2-wire synchronous system. You have a master unit, which is our PIC controller, and you have slave, which is all, this would be just I2C light sensor. We don't have any more. You have a serial data line and a serial clock line. The difference between I2C and serial is serial just like spits the data out, and I2C is all has to do with timing. Everything has to be built out, required, and made around timing. If the time's not right, nothing works. Nothing transfers, and it doesn't work. All right. This is an example of the start sequence of the I2C on the oscilloscope. Yeah, they get the one timing drop, and then the second. This is the data line, this is the clock line. So the data drops, then the clock goes, and then you can get, this is considered start bit, and then you can go and transfer some data. And then here is the ending train of the data. Right here you can see all this is low. This is your 8-bit being sent. And then when it's high 1 here, you can see that this is currently representing a 7 was sent because now you map these 3 bits to the high 1. So it says, okay, use these 3 bits only and get rid of these ones. And then it generates, this is a not acknowledged because that means that it finished its entire data train. And then you get a stop bit where the clock line goes up and then the data line goes back to high. All right. And then we did now our PIC. Our PIC we chose was a 16F1937 8-bit microcontroller. We chose this because it had many different oscillators. You can go from 31 kilohertz on frequency to 32 megahertz, which worked out perfect for us because then we could change all around to do the I2C, no problem. It has 256 bytes of EEPROM, which we definitely needed so that in case the light shuts off, it'll be written to EEPROM. We'll be able to take it back. Once the thing powers back up, we'll be able to use it again. And it operates between 1.8 volts and 5.5 volts, which was also great because that way we can fluctuate our thing. And now we're down to 3.7 operating voltage. It'll still run fine. It uses 300 microamps, which is perfect because it's still low powered, not stealing a lot from the LEDs. It has 14 channels of 10-bit analog to digital conversion, which is awesome because then we could use that for many different things. And that's also capable of SPI, I2C, UART, and LCD drivers, all kinds of stuff. So it had a lot on it for a 40-pin IC. And here's a picture of what it looks like. And then it also had a fixed voltage reference, which worked out well for a comparator circuit. You can have 1.02, 2.048, 4.06. We used a 2-volt comparator since that's when we got to 1.8 volts, it shut it down, so they wouldn't be able to save it anymore. So we used the 2 volts, so we get 2.2, cut it, save it, kind of stuff.
This is for programming. This is the actual integrated development environment we use. It's MQ Lab. We ordered the Picket 3, and it comes with a CD. It's pretty standard. It's free, standard. It has some pretty good tools on it. It has you can monitor your EEPROMs, there's buttons you can click. It has gauges and everything. It's pretty nice for free software. And the compiler we use was high-tech ANSI. We use the C language to program the device. And you can do assembly as well. Some people like assembly. And this is the actual Picket 3 programmer. It has 5 wires. It has the VCC, ground, and the data and clock pin, and the program pin. So like Dan mentioned earlier, one of the main peripherals we used was the EEPROM. And the whole idea behind that was whenever we killed the power, we wanted to store like certain data. Like we wanted to store like where our cutoff was, where like our max was, and like we used a for our time delay. And when we killed the power, we wanted to save where we were in that iteration of that time delay. So we use EEPROM. And the way it works, you only can byte write one at a time. So, and we have an example of how we took data and saved it